Now that we've had a brief reminder as to how to perform integration, let's take a look at how we can extend the concept to find the area between two curves. So we just have to make one small adjustment to the way that we integrate. And here's that adjustment. So I have these two curves now drawn, and this first curve is the same function as the previous example. All right, so I'll just call it f of x. Now, the thing is, when we did the previous example, we calculated the height of each rectangle based off of the reference point of 0 at the bottom. So f of x at a particular point tells me how tall the rectangle is, and 0 is kind of our starting point. And actually that's y equals 0 because it's a horizontal line. So the thing is, the difference between those two gave me the height of this rectangle. But here's the thing. The y-axis and the x-axis are not really important structures. They're completely arbitrary starting reference points. That's all they are. They're very convenient because 0 is a very convenient number to work with. However, it's completely arbitrary. You could use any value as an axis. You could use any constant. You could use any function as an axis. It doesn't really make any difference whatsoever. So we really just have to make one small change. And that change is, instead of using one function as the top of our rectangle and 0 as the bottom, we can use some other function to define the bottom of our estimating rectangle. And so the bottom of this rectangle will follow this curve along this path, and so it will change. And that's fine. The thing is, before, the bottom of the rectangle always stayed at 0. So we could just use f of x as the height of the rectangle. But the bottom of the rectangle changes, and that's okay. All we're interested in doing is figuring out the total vertical distance between the top and the bottom of the approximating rectangle. That's a vertical distance, and we can find that through subtraction. We just need to take f of x minus g of x. Now, usually when we think of vertical or horizontal distance, we toss absolute value around those things just to ensure that we get a positive answer, because distance is generally considered to be a physical attribute that is always considered to be positive. And that's all well and good, we can do that, but another thing we can do is, as long as we make sure that f of x is the function that's above g of x, then f of x minus g of x will always result in a positive number. So, like for instance, along this particular point here. So if I look where x is 1. Alright, so when x is 1, f of x is evaluating to 3, g of x is evaluating to -6. So the vertical distance would be f of x minus g of x, which would be 3 minus -6, telling me that there's a distance of 3 above the x-axis and a distance of 6 below the x-axis for a total distance of 9 units between those 2 points. And likewise, at 0, the thing is entirely negative, and that's okay. So when x is equal to 0, f of x is at 0, g of x is at -4, so f of x minus g of x would be 0 minus -4, which is still a positive answer. So as long as we use the curve on top as the starting point and subtract the one below, then we'll always result in a positive answer. So we're not going to use absolute value for that reason. Now, since we can get the height of an individual rectangle between these two curves, we can certainly define a width. And if we take height times width, that will give us an area of one approximating rectangle. If we do the same for all the approximating rectangles across the entire interval, so if I do all these other approximating rectangles through here, then add those together, it will give me an approximation to the amount of area trapped within these curves. And if I allow the width of these rectangles to go to 0, I can take a limit then, and I'll get the exact area trapped between the curves. So another way to think about this is a little more formal definition here. Suppose f of x is greater than or equal to g of x on an interval from a to b. All right, so this is really important. As I just mentioned, you have to have one function entirely above the other function on your interval that you're interested in. So for instance, this would be my f of x, and this would be my g of x, because f of x is higher than g of x on the entire interval from, this would be a, and this would be b. Okay? Now, the total area trapped between the functions f of x and g of x on a to b is defined as this. So we just take the integral from a to b of f of x minus g of x dx. All right, now that's a simple enough formula to work through. It's not difficult at all to perform. But to give you an idea as to why it works, let's break it down. So we know that we are able to split an integral up into two separate integrals about addition or subtraction. So that's what we do next. So effectively, I take the integral of just f of x, the function on top. And what that does is it gives me the region below f of x on this entire interval, so from a to b. So that's what I've shaded there in the blue hatch marks. Now g of x, if I did the same for g of x, it would give me all the area below g of x on that same interval, which would be this region right here. If you subtract those two, what you're left with is the area in between. And so that's effectively what we're doing. That's how we're going about computing it. We're calculating the area below the higher function, subtracting the area below the lower function, leaving us what's in between. So this representation here tells us exactly how to perform that. Now, it's important to point out that we need to make sure that one function is entirely above another function on the whole interval. If it's not, we have to break it up into sub-intervals and work it that way, because the thing is, you can get cancellation of areas, you can get negative areas otherwise. And there's always a question here about negative areas. And the thing is, I try and differentiate the language of negative areas versus negative integrals to kind of help you understand what I mean when I'm talking about things. When we are doing an application problem involving area, we use an integral to calculate that area. Area is a physical dimension that's defined to always be positive. So when I'm talking about area, the answer has to be positive. However, integrals are not necessarily always going to be interpreted as areas. There's different ways of interpreting integrals. And there might be very good reasons why you need an integral to be a negative value. So when we talk about integrals, negative integrals are allowed. But when we're calculating area, we need to make sure everything stays positive. So it's really in the language that you need to watch out for to make sure you know when you're allowed to come up with a negative answer, or allow cancellation, or you're not allowed. So this next question says, calculate the total area trapped between the curves f of x equals x over 2 plus 5 and g of x equals x plus 1/2 on the interval from 1 to 5. Okay, so in order to work this through, I've already gotten us started by graphing these functions, and to help us know which one's which, it's pretty straightforward. They're both linear. F of x has a y-intercept of positive 5, so that's going to be this curve right here. And then g of x has a slope y-intercept of 1/2, so that's clearly going to be this function right here. All right, so what I'm looking for is on the interval of the x-axis from 1 to 5. That's going to be from here to here, which gives me a left and right bound. And those are straight vertical lines. And I'm looking for the area that's trapped between those things, which is this region right through here. Okay, so to come up with the area of that region, what I'm told is that I can find it by doing an integral from the lower x starting point to the upper, and then taking f of x, which is going to be the function on top, minus the lower function, dx. So in this case, it would be the integral from 1 to 5. F of x is x over 2 plus 5. And then we'll subtract g of x, which is x plus 1/2. And this is going to work out fine because f of x is entirely above g of x for this whole interval. All right, now, as we have learned, you can use f in int in order to help speed up these calculations. So if you want to grab your calculator at this point, it might be useful for you to do a little bit of simplification, because there are some things you could run into. So for instance, let me show you. If I go under math and then hit 9, which gets me f in int, lower bound and upper bound, no problem, those were just given. Inside my integral here, I would need to take x over 2, oh, not x minus 2, x over 2, plus 5. And then the thing is, it's really easy for students to get in trouble with this minus here, because it's in front of a set of parentheses, which means the distributive property takes over, and it needs to make sure it distributes to both pieces. It's probably a good idea to take a minute to do a few simplifications before you start using the calculator. So for instance, if I subtract x in there, or distribute the negative, that is, then I have some like terms that I could combine. A little bit of work with fractions, however, or I could just plug it into the calculator at this point. It doesn't really make a whole lot of difference. But x over 2 minus x, which would be effectively 2x over 2, would give me negative x over 2. And then 5 minus 1/2 is going to be 4.5, or 9/2. So plus 9/2 dx. And I could plug that in. That's totally fine. Either way, just make sure you don't mess up that negative. It's extremely common. So what I would probably do is just mentally distribute that in my head and say that's minus x and minus 1/2, or really just 0.5. Then we're integrating with respect to x. So when we press enter, it will come up with an answer for us, In this case, it happens to be an integer. If it was not an integer and it was a fraction, we of course could convert that. So that's equal to 12. So that total area is equal to 12. Now, what's happening behind the scenes here? Well, what's happening is we're taking these two functions and combining them using a function operation. And you learned about function operations probably back in a college algebra course when you studied functions. And the result of that gives us a new function. And that new function, if we take a look at it, so it's got a y-intercept of 9/2, so that's 4.5. And then it has a slope of -1/2. So if I go down 1 over 2, there's another point. Down 1 over 2, there's another point. Down 1 over 2, and so forth. I'm just trying to get a few points here. That gives me a function like this. All right, and what I'll do is I'll say this is effectively some new function, h of x. All right, now, what's interesting about h of x is that h of x represents, if I looked at a rectangle on any point of this interval, h of x represents the height of that rectangle at every single point. So the distance between 6 and like 2.5 is going to be 3.5. So the height of this function here is 3.5. So the height of this function is always going to be the difference between these two functions. So the total area under this curve is going to be the same area as the total area trapped between these two curves. And so that's effectively what we're doing, is we're transforming this region into a new function whose integral itself is equal to the area trapped between those two curves. That's effectively what's going on here. Let's take a look at another example. All right, so in this one, we have R is the region bounded above by the graph of f of x equals x, and below by the graph of g of x equals x to the fourth. Find the area of region R. All right, so f of x equals x. That's clearly this function here. So that's f of x. And then the other function is going to be my g of x, which is x to the fourth power. So the region that I'm interested in is bounded above, so the highest points of this region is determined by f of x, and bounded below by x to the fourth. So bounded means it's a finite region that you could draw a circle around, and that's what's bounded between these two graphs. Okay? So I want to find the area of this region R. So the area of that region could be found integrating between, I need two endpoints here. And so the endpoints are going to be the intersections of these curves. So here's one clearly at x equals 0. Here's another one here at x equals 1. If it wasn't quite so evident where those two curves intersected, you could certainly set them equal to one another. So x equals x to the fourth, and then solve. And there's not really much here to solve, so I would have like 0 equals x to the fourth minus x, or 0 equals x times x cubed minus 1. And so this would lead to x being 0. And if I took x cubed minus 1 and set that to 0, I could say x cubed equals 1, or taking the cube root of both sides, x equals 1. All right, so that gives me those 2 points. Just, you can always find the intersection of two curves by setting them equal to one another and solving. All right, now I need to take the upper function minus the lower function and and subtract. So the upper function is always x in this case. The lower function is always x to the fourth. All right, now, when I integrate, and sometimes it's easier to use the calculator, sometimes it's actually easier to just simply integrate. This one's probably arguable as to which will take more time, but I'll go ahead and use this just because. All right, so I'm integrating from 0 up to 1 of x minus x to the fourth dx. So I get 0.3, which would be the same thing as 3/10. And that's the total area of that region R. And it's always good to just kind of state where you got that answer from. So we used f in int, so let's go ahead and state that that's where that came from.